Here are some problems where we use Coulomb's law to compare electric forces. Two charges, Q1 and Q2, are separated a distance r. The force they feel is F. Well, let me write that down. Coulomb's law says if you plug in the two charges, and those are just Q1 and Q2 is what they've told us, and you divide by the distance squared, which they're just calling r for the simple first case, you multiply by the constant, you get the electric force, which they're calling F for this first case. Oops, just F. What is the force? Okay, so there's some new force we're going to talk about here. I'll call that F2. What is the force between two charges, 2q1 and 4q2, that are placed a distance 3r apart? Well, I need to write Coulomb's law again. Now the values here are different. It's not q1 here. That charge is not the same as what it was before. It's twice the original value, 2q1. So let me write that down. And this other charge in the second case, this next charge is not q2. It's not the same as it was before. It's 4 of the original q's. And similarly, the distance is not the same r as before. It's they're 3 times as far apart. Now it's really important that the 3 is inside the parentheses. If you just write this, then you're only tripling r squared. You're not tripling r itself, because the square wouldn't apply to the 3 if you write it this way. So to make sure we're doing this correctly, we have to make sure the parentheses are around the 3. When we have two things in parentheses, we distribute the squaring to both factors. And what do we get now? Well, we've got in the numerator a k, we've got a 2 right there, we've got q1, we've got a 4, and we've got q2. In the denominator, we have 3 squared, that's 9, and we have r squared. But wait a second. The original k, which I see here in my second equation, the original q1, which is also here in my second equation, the original q2, and the original r squared, all together are equal to that force F. So these 4 things are equal to F, and I can substitute. I will replace the highlighted things. I'm going to replace those with F. And what do I still have? Well, I've got a 2 in the numerator, a 4 in the denominator, and a 9. I'm sorry, 2 in the numerator, 4 in the numerator, and a 9 in the denominator. So F2, the second force, is equal to 8/9 of the original force, F. That's our answer. Here's another one that's the same process, just a little more complicated. A first charge, Q1, is placed a distance r from a second charge, Q2. The force they feel is 90. Okay, Coulomb's law says when you plug in the two charges, which we're calling Q1, Q2, divide by the distance, which is just called r in this case, squared, and you multiply by the constant k, you get the force, which they're telling us is 90. What is the force between two new charges? So there's some new force, which I'll just call F2. And the new charges are not Q1 and Q2. They're not the original values. They are, 3 Q1, so 3 of the original Q1. And the second charge is half of the original Q2. And how far apart are they? R divided by 2. They're half the distance apart. So we expect the force to be different. The first thing I always do is distribute the square to both things in parentheses. And here's how I'm going to write that. K times 3 times Q1 times Q2. I've got a 1/2 here in the numerator divided by 2. That's the same as multiplying by 1/2. And that's all divided by r squared over 4, which is just 2 squared. But instead of dividing by this, let me multiply by the reciprocal, 4 over r squared. And just like before, k q1 q2 over r squared, k q1 q2 over r squared, those four things are equal to 90. So if I calculate this out, I've got 90 times 3 and then divided by 2 times 4. If you do that calculation, 90 times 3 times a half times 4, what you get is 540 newtons. That's our answer.